All right, welcome to the Explainer. Have you ever had one of those days, you're just completely wiped out, totally exhausted, but if you asked a physicist, they might tell you you've done zero work all day? Yeah, really. Today, we're going to dig into the surprising definitions of work and power. It turns out physics has a really specific and, honestly, kind of weird way of looking at what it means to actually get something done. So let's just jump right in. What do you think of when you hear the word work? For most of us, it's probably, studying for a big test or maybe just pushing through a tough day at the office. But how does our everyday idea of work really stack up against the hard and fast rules of physics? Let's find out. Okay, so on one side, you've got our everyday definition of work. Studying for a test, pushing against a wall that just won't budge, or even just holding a heavy bag still. We'd call all of that hard work, right? But then there's the physics definition. And in that world, work is only happening when you're doing stuff like lifting a box, pushing a shopping cart, or pulling a wagon. The key difference? Something's got to move. And this is where it gets really wild. So, let's say you spend an entire hour pushing against a solid brick wall with all your might. You're sweating, your muscles are screaming, and a physicist would just walk by, look at their clipboard, and say, "Nope, sorry, zero work done here." Seriously, no movement, no work. It's a total mind-bender, isn't it? So what is work, really? If all that effort against a wall doesn't count, what does? Well, let's break it down. It turns out there are two secret ingredients you absolutely have to have. Okay, so here it is, the official definition. Work is done when a force, and that's just any push or a pull, acts on an object and makes it move. Or, to use the fancy physics term, causes its displacement. The bottom line is just this. If nothing moves, no work is done. That's the golden rule. So really, it all comes down to these two things, and you gotta have both. First, you apply a force to something, a push, a pull, whatever. And second, that something has to actually move a certain distance. If you're missing one of those two ingredients, you just don't have work. Simple as that. All right, let's talk more about these two key ingredients. Because, it's not quite as simple as just having a force and a movement. Oh no, the direction of everything turns out to be absolutely critical. Check this out. When the force you're applying and the direction the object moves are lined up, like you're pushing a box forward and it moves forward, we call that positive work. Pretty straightforward, right? But now look at the other example. Think about friction. Friction is always trying to stop things, right? It's a force that works against the direction of motion. So because its force is pointing the opposite way, we actually say that friction does negative work. Cool, huh? Okay, so now that we're thinking about direction, let's look at when work equals zero, because this leads to another one of those really weird physics situations. A scenario where you can have a force and you can have movement, but the amount of work is still a big old zero. So what happens when the force and the movement are perpendicular to each other, at a right angle? Let's paint a picture. Imagine you're carrying a heavy bag of groceries home. Your arm is pulling up on the bag to keep it from hitting the ground, but you are walking forward. See that? The force is vertical, but the movement is horizontal. And this diagram shows it perfectly. The force is pointing straight up, but the displacement, the movement, is going forward. They're making a perfect 90-degree angle. And here's the physics rule. Whenever the force and the direction of motion are perpendicular like this, the work done by that specific force is, well, you can probably guess. Yep, zero. A big fat 0 joules. Isn't that crazy? Your arm is getting tired. It feels like you're working hard just holding that bag up. But because the force from your arm is only going up and not forward, it's doing zero work in the direction you're walking. Now, to be clear, your legs are definitely doing work to move your whole body forward, but your arm, in the eyes of physics, it's just along for the ride. Okay, so I think we've got a pretty good grip on work now. It's all about force causing movement in the same direction. So let's level up. Let's add a new ingredient to the mix. Speed, or more specifically, time. Let's talk about power. And to really get what power is all about, let's set up a little friendly competition. So here we have Nathan and Jesse. They're both weightlifters, and they're about to do the same workout. Let's see what happens. So here's the deal. Nathan lifts a 40-kilogram barbell 10 times, and it takes him a full minute, 60 seconds. Now Jesse comes along. He lifts the exact same 40-kilogram barbell for the exact same 10 reps, but he just crushes it. He finishes in only 10 seconds. All right, time for a pop quiz. Based on everything we've learned so far about the physics definition of work, who did more work, Nathan or Jesse? Think about it for a sec. If you said they did the same amount of work, you are absolutely right. It's a bit of a trick question, I know. But remember, work is just force times distance. Since the force, the weight of the barbell, was the same, and the distance they lifted it was the same, the total work done is identical. Physics work just doesn't care how fast you do it. Okay, but come on. Clearly, Jesse's performance was way more impressive, right? So if it's not about work, what is it about? This is where power enters the picture. So, who was more powerful?
Jesse. No question about it. Jesse is way more powerful. And why? Because he did the same amount of work in a tiny fraction of the time. And that, right there, is the whole secret to power. It's all about how fast you get the work done.
So here's the textbook definition for you. Power is the rate at which work is done. Basically, it's a measure of how quickly you can perform that work. So it's not just about what you're doing, it's about your speed. If you want to get mathematical about it, just think of it as the amount of work you do divided by the time it takes you to do it. All right, let's look at work versus power out in the real world, because this isn't just some abstract physics puzzle for weightlifters. This difference is absolutely fundamental to engineering, and honestly, it explains how a ton of the stuff in our modern world actually works. So why does any of this matter? Well, think about a sports car. We say its engine is powerful, right? What we really mean is that it can do a huge amount of work, moving the car, in a really short amount of time. Or think about an elevator. It's got to be powerful enough to do the work of lifting a bunch of people really, really quickly. Same goes for power plants. They're rated by how much work they can do over time to generate all the electricity we use. It's the same idea everywhere you look. So really, it all just boils down to this simple idea. High power means you can cram a lot of work into a short amount of time. Low power means it's going to take you longer to get that same work done. That's it. It's the ultimate measure of performance for pretty much everything, from a car engine to the processor in your phone. So let's wrap it up. Work is what moves our world, literally, and power is what determines how fast it all happens. But that leaves us with one big, hanging question, doesn't it? What is the fuel that makes it all possible? Where does the ability to even do work come from in the first place? Well, that sounds like a question for our next explainer.